2 seconds. That is the entire window. An F/A-18 Super Hornet, fully loaded, weighing close to 50,000 pounds with fuel and weapons aboard, sits on the bow of the USS Gerald R. Ford. The catapult fires. In roughly 2 seconds, across about 300 feet of steel deck, that aircraft goes from a dead stop to flight speed, around 160 miles per hour, and leaves the ship. The numbers are almost hard to believe. The force involved is enormous. Making it repeatable, launch after launch, for decades, is one of the genuine achievements of modern naval engineering. So here's the question at the center of this story. If the catapult can do that, throw 50,000 pounds into the sky with that kind of precision, why does the same system run into serious trouble when asked to launch something far lighter? A drone. An unmanned aircraft that might weigh a few hundred pounds or a few thousand. Something the Navy increasingly needs on that same deck for the same missions, launched from the same rail. The catapult that hurls a manned strike jet without hesitation becomes, at the lighter end of the weight scale, a system that engineers have had to rethink almost from scratch. That is the paradox. The answer lives inside the physics of what a launch system is actually doing. Not just throwing weight, but managing energy transfer at the edges of a very narrow envelope. We are going to walk through exactly how that envelope works, why it breaks down at the extremes, and what it means for the carrier air wing the Navy is trying to build right now in the Western Pacific. The short version is this. The USS Gerald R. Ford and its EMALS system were designed around a specific class of aircraft: heavy, manned, expensive jets. The future the Navy needs involves something radically different. Getting from one to the other is not just an engineering problem. It is a budget problem, a strategic problem, and a question about what a carrier deck is actually for. We will get there. But first, the machine itself. The aircraft carrier has one fundamental job: project air power far from shore. Everything else on the ship, the reactors, the crew of roughly 5,000, the defensive systems, the fuel and ordnance stored in the hull, exists to support that single function. And the mechanism that makes it possible, the device that bridges the gap between a stationary deck and flight speed, is the catapult. For most of carrier aviation's history, that meant steam. A steam catapult works by storing high-pressure steam in accumulators, then releasing it suddenly into a piston that runs along a track in the deck. The piston connects to a shuttle, the shuttle connects to the aircraft, and the whole assembly accelerates down the track. It is violent, loud, and it works. The Nimitz-class carriers: USS Nimitz, USS Ronald Reagan, USS Carl Vinson, USS Abraham Lincoln, and the rest of the class, have used steam catapults for decades. Across millions of launches, the system proved reliable enough to build an entire doctrine around. But steam has limits. The energy in a steam shot is hard to precisely calibrate. The system runs at high temperature and pressure, which means maintenance demands are significant. And the weight range that steam handles well is relatively fixed. Light aircraft get too much energy. Heavy aircraft push the upper boundary. The system works well for the middle, which, during the Cold War and into the 1990s and 2000s, was exactly where most carrier aircraft lived. Then the Navy decided to replace steam entirely. The Electromagnetic Aircraft Launch System, EMALS, is the centerpiece of the Gerald R. Ford-class carrier program. Instead of a steam piston, EMALS uses a linear induction motor, a long track of electromagnets that accelerate a carriage down the catapult stroke. The energy comes from a flywheel energy storage system, charged between launches and discharged in a precisely controlled ramp. The theoretical advantage is real. EMALS can tune its energy output across a much wider range than steam. The design specification called for handling aircraft from around 10,000 pounds all the way up to 100,000 pounds, a tenfold weight range. Steam catapults on Nimitz-class ships work across a narrower band. On paper, EMALS was supposed to be the system that could finally handle both the heaviest strike jets and the lightest drones from the same deck. The USS Gerald R. Ford itself, CVN-78, commissioned in 2017, was the first ship to carry it. The program cost and schedule had already run into trouble by that point. EMALS development ran years behind and hundreds of millions of dollars over initial estimates. But the system was working, and the Navy pressed forward. The Gerald R. Ford class is now the backbone of the future carrier fleet. Here's what the numbers looked like in early service. EMALS was designed to a reliability target of 1 critical failure per roughly 4,500 catapult cycles. In testing and early deployment, the actual rate ran significantly worse. 1 failure per roughly 200 to 400 cycles, depending on the period and the reporting. The Navy and the manufacturer, General Atomics, worked through a long list of design modifications. By the mid-2020s, reliability had improved substantially. But the early record created a credibility problem for the program. The system that was supposed to expand the launch envelope was struggling to deliver consistent performance even within the weight range it was primarily designed for. What no one fully advertised at program launch was how the physics of the light aircraft problem was going to play out in practice. Because the weight range specification is real. EMALS can theoretically handle much lighter loads than steam. But handling a light load and doing it reliably, repeatedly, without damaging the aircraft or the system, are different things. Understanding why requires going one layer deeper into what a catapult is actually managing. Here is what strikes most people as surprising. If a system is strong enough to launch a 50,000-pound jet, a 500-pound drone should be trivially easy. Just dial the power down. But that is not how it works. The challenge is not raw power. It is control. A catapult launch is not just an acceleration event. It is a coupled system. The aircraft has a holdback fitting at the rear, which restrains it until the catapult reaches the correct tension. It has a launch bar at the front, which connects to the catapult shuttle. When the catapult fires, the shuttle accelerates, the holdback releases, and the aircraft goes with it. At the end of the stroke, the shuttle decelerates, abruptly, while the aircraft continues forward and off the deck. The transition from attached to free flight happens in a fraction of a second, and the aircraft needs to be moving at exactly the right speed at that moment. Fast enough to fly, not so fast that it overstresses the airframe or the launch fittings. For a heavy aircraft like the F/A-18 Super Hornet, the system has a lot of physics to work with. The mass of the aircraft provides inertia. There is plenty of time, proportionally speaking, for the energy transfer to be managed across the stroke. Small variations in the catapult's energy output get absorbed by the aircraft's mass. The coupled dynamics are relatively forgiving. For a light drone, the margins collapse. A few percent variation in energy output, normal for any electromechanical system, represents a much larger fraction of the total kinetic energy needed. The shuttle has to decelerate at end stroke while transferring a much smaller mass, which makes the handoff dynamics more sensitive. The launch bar interface, designed and sized for manned aircraft loads, may not be compatible at all with a lightweight airframe, and the speed tolerance at end stroke. The window between too slow to fly and too fast for structural integrity can be very narrow for an aircraft not originally designed for catapult launch. The MQ-25 Stingray is the clearest real-world example of how the Navy is navigating this. The MQ-25 is an unmanned carrier-based aerial refueling aircraft built by Boeing, designed to operate from Gerald R, Ford-class, and Nimitz-class carriers. It weighs roughly 60,000 pounds at maximum takeoff weight, which puts it squarely in the heavy aircraft category. The MQ-25 does not represent the light drone problem. It represents the Navy's pragmatic first step. Build an unmanned aircraft that fits the existing catapult envelope, rather than redesigning the catapult to fit the drone. That is a meaningful strategic choice. The MQ-25 program cost runs in the range of $13 billion for the initial fleet. Each aircraft costs in the range of $60 to $80 million. For that money, the Navy gets an unmanned tanker that extends the range of the carrier air wing by removing the refueling burden from manned aircraft. It is valuable. But it is also essentially a conventional aircraft without a pilot. Not the kind of cheap, expendable, mass-producible drone that military planners are increasingly building doctrine around. The drone the Navy also wants on the carrier deck looks very different. Small, relatively inexpensive, potentially expendable. The kind of platform that makes sense for ISR missions, electronic warfare, or attriting an adversary's defenses before manned aircraft enter the threat envelope. The economics are the entire point. A small tactical drone might cost tens of thousands of dollars. An MQ-25 costs 60 to 80 million. An F/A-18 Super Hornet costs around $67 million per aircraft at recent procurement prices. An F-35C, the carrier variant of the Joint Strike Fighter, runs higher still, in the range of $90 to $100 million per aircraft. The carrier air wing today is built around a handful of very expensive platforms. A typical carrier air wing might include 4 to 5 squadrons of strike fighters, F/A-18E and F Super Hornets and F-35Cs, plus electronic warfare aircraft, early warning aircraft, helicopters, and now the MQ-25 tanker. The total number of aircraft on the deck at any given time is measured in the dozens, not the hundreds. Each one represents a significant capital investment, a highly trained aircrew, or, in the MQ-25's case, a sophisticated system requiring significant maintenance infrastructure. What the light drone concept offers is fundamentally different arithmetic. Instead of launching a single F/A-18 Super Hornet to prosecute a target, you might launch 20 small drones, some expendable, some recoverable, to overwhelm a threat, saturate defenses, and accept attrition losses that would be catastrophic if applied to manned aircraft. The cost-exchange ratio shifts. The adversary's expensive interceptors are spent against cheap platforms. But only if you can actually get those drones into the air, from the deck, at the tempo the operation requires. One detail that stuck with me when going through the technical documentation on this: the EMALS design specification for weight range was always broader than what Steam could do. That was the selling point. But the specification and the operational reality are not the same thing. A system rated to 10,000 pounds minimum launch weight, in practice, may have a much narrower window where it operates reliably and without damaging the aircraft. The testing regime that qualifies a new aircraft for catapult launch is extensive precisely because the forces at end stroke are severe. A light drone, unless it was designed from the ground up for catapult launch, may simply break. So the loop closes here, at least partially. The catapult built to replace Steam, supposed to expand the envelope, has, in its first decade of service, mostly been used to launch the same class of aircraft that Steam launched before it. Heavier unmanned aircraft like the MQ-25 fit within that envelope. Lighter drones largely do not. And the question of what to do about that is now a live operational and procurement problem. Here is where the path divides. Option 1. Retune EMALS for lighter aircraft. This means engineering work on the shuttle interface, the holdback and launch bar fittings, the energy profile at the low end of the stroke, potentially redesigning components already embedded in a commissioned warship. The USS Gerald R. Ford and CVN-79 John F. Kennedy are already in service. CVN-80 Enterprise and CVN-81 Doris Miller are under construction. Any retrofit to EMALS on ships already delivered is expensive and operationally disruptive. Any redesign for ships still under construction adds cost and potentially delays delivery. Option 2. Keep EMALS for heavy aircraft and develop alternative launch methods for light drones. Several candidates exist. Pneumatic launchers, essentially scaled-up versions of what shore-based drone operators use, can be fitted on deck or on sponsons without major ship modification. Rail launchers, slingshot systems, even vertical launch concepts adapted from land-based platforms. The advantage is that you do not touch the EMALS installation. The disadvantage is that you are adding complexity to a deck that is already one of the most complicated operational environments on the planet. Option 3. Design the drones differently. Build carrier-capable light drones from the beginning to handle catapult launch loads. This means accepting structural weight penalties that reduce the mass advantage of small drones, or accepting that the launch interface adds cost that narrows the economics gap. None of these options is free. Each trades a different combination of cost, timeline, and operational risk. And the background pressure driving all of them is the same. In the Western Pacific, the threat environment that carrier air wings are being designed to operate against is changing faster than any single procurement decision can track. Beijing's shipbuilders have put 2 carriers into service in the past decade, the Liaoning and the Shandong, and the Fujian, the Type 003, is the first Chinese carrier to carry an electromagnetic catapult system of its own. The Fujian uses CATOBAR, catapult-assisted takeoff, barrier-arrested recovery, the same basic concept as the Gerald R. Ford. Beijing's investment in carrier aviation suggests that whatever problems EMALS has encountered on American decks, the electromagnetic catapult concept itself is considered viable enough that China's naval planners adopted it independently for their most advanced carrier. That is worth sitting with. Against that backdrop, the U.S. Navy's carrier is expected to operate within range of DF-21D and DF-26 anti-ship ballistic missiles, weapons specifically designed to threaten surface ships at extended range. The DF-21D, has a stated range of around 1,500 kilometers. The DF-26 extends that to around 4,000 kilometers. The operational implication is that a carrier in the Western Pacific operates inside a threat envelope that did not exist a generation ago. The carrier's aircraft need to reach targets at range, while the ship itself stays as far from the threat as possible. That pressure on range is one reason the MQ-25 tanker matters. It extends the effective reach of F/A-18 Super Hornets and F-35Cs without requiring the ship to move closer to the threat. But it also underlines why cheap, expendable drones matter. If the threat environment makes every manned aircraft sortie a high-risk event, having unmanned platforms that can absorb attrition changes the calculus. Here is the economic layer that makes this more than an engineering question. The USS Gerald R Ford cost approximately $13 billion to build. That number covers the hull, the reactors, the weapons systems, the EMALS installation, the advanced arresting gear that catches returning aircraft, the sensors, the communications systems. Everything. It does not cover the air wing, which adds several billion more. It does not cover the destroyers and cruisers of the carrier strike group that escort the ship. It does not cover the submarines that typically operate in coordination. A fully deployed carrier strike group, when you account for all supporting assets and operating costs, represents a concentration of national investment without parallel in any other military platform. That investment was optimized around a specific air wing, not the air wing of 2035 or 2040. The air wing of the 1990s and 2000s, when the F/A-18 Super Hornet was the primary strike asset and mass unmanned platforms on a carrier deck were speculative. EMALS was a significant upgrade within that framework, but the framework itself may be the constraint. Here is the take that will probably get pushback. The EMALS light drone problem is not really a catapult problem. It is a design philosophy problem. The Gerald R. Ford was designed as the most capable version of a carrier concept that dates to the mid-20th century. A ship that launches a relatively small number of very capable, very expensive aircraft. The drone future that Navy planners are increasingly serious about requires something different. A platform that can generate high sortie rates of cheap, expendable, mass-producible aircraft. Those two design philosophies pull in opposite directions. You can try to make the Ford class do both, and engineers are working on exactly that. But there is a real argument that the next carrier class, whatever comes after Ford, needs to be designed around the drone from the beginning, not retrofitted to accommodate it. What would you do with that $13 billion if you were starting from scratch today? That question is not rhetorical inside the Pentagon. It is a live budget argument. The Navy's 30-year shipbuilding plan has to balance Ford-class carriers, enormously capable but expensive and relatively few, against the broader fleet structure that includes Arleigh-Burke-class destroyers, Virginia-class attack submarines, amphibious ships, and the logistics train that keeps all of it operating forward. Every dollar spent maintaining and upgrading the carrier launch envelope is a dollar not spent somewhere else in that force structure. The obstacle EMALS faced in early service was not the light drone problem. It was basic reliability. Between roughly 2017 and 2022, the system's mean cycles between critical failures ran far below the design target. The fix required not one redesign, but a sustained engineering campaign involving General Atomics, Newport News Shipbuilding, and the Navy's own systems command. What is instructive is how that process unfolded. Each failure mode was isolated, a hardware or software change was implemented, and the system was retested. By the early 2020s, reliability had improved to the point where the system was meeting operational requirements, if not always the original specification targets. The same iterative process is now underway for the light drone interface. Navy engineers and researchers at facilities, including the Naval Air Warfare Center Weapons Division, have been working on the technical requirements for what a carrier-launched light drone needs to survive the catapult stroke. The answer involves changes to both the aircraft and the interface. Lightweight launch bars rated for the correct load, energy profiles tuned for the lower mass range, and holdback systems that release cleanly at the correct moment for a lighter airframe. None of this is classified in principle, but none of it is solved either. Here is the part that does not sit right, even now. The EMALS specification, the document that defined what the system was supposed to do, always included light aircraft in the design envelope. The engineers who wrote it understood the physics. They knew the linear induction motor could, in principle, handle a 10,000-pound aircraft as well as a 100,000-pound one. The gap between what the specification said and what the fielded system can do reliably is not a gap in imagination. It is a gap in the interface. The physical connection between a generic launch rail and the specific structural and aerodynamic requirements of aircraft that were never part of the original design trade space. You can put a number on a capability chart. Getting real hardware on both ends of that line to work together is a different problem entirely. The MQ-25 Stingray has completed carrier qualification trials and entered low-rate initial production. The first operational aircraft are expected to deploy with carrier air wings in the mid-2020s. When they do, the carrier air wing gains a tanker asset that adds meaningful range to every F/A-18 Super Hornet and F-35C on the deck. That is a real capability improvement. But it does not close the gap on the light drone question. The Stingray is heavy enough to fit the Catapult. The drone that comes next, smaller, cheaper, expendable, may not be. The Navy's light tactical unmanned aerial vehicle programs and the broader family of systems being evaluated under the Unmanned Carrier-Launched Multi-Role System concept have been working toward exactly the light drone launch problem. Various concepts have been tested at shore facilities, using rail launchers and modified catapult interfaces. Some of those tests have been successful in a limited sense. The aircraft survived the launch. Whether any of them are ready for fleet-wide deployment at operational tempo from a carrier at sea in the Western Pacific is a different question. What strikes the analysts who follow this program is not the technical difficulty. Every hard problem in carrier aviation eventually gets solved. What is notable is the timeline. The drone threat that a carrier air wing might face, small, cheap, mass-launched from surface ships or from shore, is available to adversaries right now. The Chinese People's Liberation Army Navy has been investing heavily in drone systems, both for reconnaissance and for potential offensive use. The timeline for fielding an effective counter to that threat, or for fielding a comparable capability on the American side, is measured in years. The gap between the threat's development pace and the acquisition system's pace is itself a strategic variable. Put yourself in the position of the Carrier Strike Group commander for a moment. You have 11 ships, approximately 65 to 70 aircraft in the air wing, 5,000 people aboard the carrier alone. Your operational orders place you in the Philippine Sea, within nominal range of DF-26 missiles from the mainland. Your F/A-18 Super Hornets and F-35Cs can reach targets at range, particularly with MQ-25 tanking support. Your Arleigh Burke-class destroyers carry SM-6 interceptors and can defend against incoming missiles in the terminal phase. Your Virginia-class submarine is operating independently in coordination with your tasking. What you do not have, in the near term, is the ability to mass-launch cheap, expendable drones from your carrier deck via catapult. You can fly the MQ-25. You can potentially use deck-mounted pneumatic launchers for very small systems, accepting the operational overhead of managing a separate launch infrastructure. But the vision of a carrier that can generate 100 sortie days, mixing manned jets and expendable drones through the same catapult system. That vision is ahead of you in time, not behind you. The EMALS reliability improvements bought back credibility for the program. The MQ-25 bought a real operational capability. The light drone catapult problem is the next layer, and it has not been solved in the way the system's advocates originally promised. The cost numbers tell part of the story. EMALS development ran to roughly $900 million over its original budget before the program stabilized, the total Gerald R. Forward program cost is approximately $13 billion for the lead ship alone. Subsequent ships in the class cost less, as shipbuilders at Newport News Shipbuilding work down the learning curve, but the program total across 4 ships runs to tens of billions. Against that investment, the cost of a small tactical drone, $10,000 to $50,000 for some categories, seems almost negligible. But getting that drone reliably off the deck of a carrier, at sea, under operational conditions, requires interface engineering that costs money too. The cheap drone is only cheap in the air. Getting it there is not. Here is where the loop closes completely, and the answer to the opening question becomes clear in all its dimensions. A catapult throws a heavy jet fine because the jet was designed alongside the catapult. The F/A-18 Super Hornet, the F-35C, the E-2D Advanced Hawkeye. Every aircraft certified for carrier launch carries structural reinforcements, interface hardware, and aerodynamic characteristics that reflect decades of co-evolution with the catapult system. The launch envelope is not a range defined by physics alone. It is a range defined by the aircraft catapult interface. And every aircraft in that envelope has been engineered specifically to live within it. The light drone, as a category, has not gone through that coevolution. It was developed outside the carrier aviation ecosystem for different launch concepts: pneumatic rails, ground launch, airdrop. Bringing it onto the carrier deck means either redesigning the drone to survive catapult loads, adding structure and weight that narrow its cost advantage, or redesigning the catapult interface to handle loads it was not originally optimized for on a ship that is already commissioned and in service. Both paths are being pursued simultaneously. That is the honest answer. The Navy is not choosing one or the other. It is running parallel engineering tracks, working on light drone-compatible catapult interfaces for Gerald R, Ford-class ships, while also developing alternative launch methods that do not require a catapult. The timeline for either track to produce a fleet-ready capability is several years at minimum. What this means for the carrier as a strategic instrument is significant. The aircraft carrier's value has always rested on its flexibility, the ability to project a range of air power options from a single mobile platform. If the light drone gap persists into the 2030s, the carrier's flexibility relative to a threat that is rapidly adopting cheap mass launch concepts narrows, not catastrophically. The F/A-18 Super Hornet and the F-35C remain powerful aircraft. The MQ-25 tanker adds real range. The strike group as a whole retains enormous capability. But the gap exists, and it is not invisible to the planners on the other side of the Pacific. The Gerald R. Ford-class program also carries a specific institutional lesson worth naming directly. EMALS was sold partly on the promise of an expanded weight envelope. The ability to handle aircraft the steam catapult could not. That promise drove part of the justification for a program that ran over budget and behind schedule. In the years since the Ford commissioned, the system's actual contribution to expanded capability has been limited primarily to reliability improvements and operational experience with the same aircraft type steam already handled. The light drone capability, the novel part of the value proposition, remains aspirational. What this tells us about large defense programs is not surprising to anyone who follows them, but it is worth saying plainly, a specification is not a capability. A system rated to handle a 10,000-pound aircraft and a system that can reliably, repeatedly, safely launch a 10,000-pound aircraft at sea in operational conditions are two different things. The gap between them is where programs spend years and hundreds of millions of dollars. The parallel on the Chinese side is instructive in a different way. The Fujian, the Type 003 carrier, was designed with electromagnetic catapults from the beginning. Not retrofitted, not upgraded from steam, but built new with the launch system as a core element of the design. Beijing's shipbuilders are operating without the legacy constraint of a steam catapult fleet to transition from. Whatever problems they encounter with their EMALS equivalent system, and they will encounter problems, the physics does not change because the flag is different. They face them with a clean sheet design rather than a retrofit. That is not an argument that China's carriers are superior. The US Navy has decades of operational experience with carrier aviation that no other Navy can match. But it is a design philosophy point. The Gerald R. Ford is the best version of a mid-20th century concept. The question for the 2030s is whether the best version of that concept remains the right center of gravity for naval power projection in a contested Pacific. There is a pattern worth observing at this point in the analysis. Every time the Navy has faced a fundamental technology transition in carrier aviation, from propeller aircraft to jets, from conventional to nuclear propulsion, from steam to electromagnetic catapults, the transition has been expensive, slower than planned, and ultimately successful. The Nimitz class carried nuclear reactors that were technically unprecedented. The steam catapult that replaced hydraulic launchers required years of development and operational refinement. Every major system on a carrier has a history of being harder than expected and taking longer than scheduled. The light drone catapult problem fits that pattern. It is real. It is not solved. It will eventually be solved because the physics permits it and the operational need is clear. The timeline and the cost are the variables that remain open. What the pattern also shows is that the Navy rarely abandons a concept because the first implementation is hard. EMALS is not going to be removed from Gerald R. Ford-class carriers. The light drone interface will be engineered, qualified, and eventually deployed. The question is whether the pace of that engineering matches the pace of the threat environment. The crew dimension is one that does not always make it into the technology discussion but matters operationally. A carrier deck is a confined, high-energy environment. Every aircraft type on the deck requires trained handlers, specific tool sets, compatible interface hardware. Adding a new category of aircraft, light drones with different launch interfaces, different maintenance requirements, different handling procedures, adds complexity to a crew already managing one of the most demanding operational environments in the military, the USS Gerald R. Ford has been working toward a reduced crew size compared to Nimitz-class carriers, using automation to offset manpower. Adding new drone categories runs against that trend unless the drones themselves are designed with minimal deck footprint in mind. This is an obstacle that does not get as much attention as the catapult physics, but it is real. The carrier air-wing integration process. Getting a new aircraft type qualified for carrier operations, training the deck crew, establishing the maintenance pipeline, takes years even for aircraft that fit the existing launch envelope cleanly. A light drone that requires a modified launch interface adds another layer to that integration timeline. The strategic cost, stated plainly, is this. The United States Navy has the most capable carrier aviation force in the world. The Gerald R. Ford-class carriers are the most advanced large-deck carriers ever put to sea. The F-35C is a fifth-generation strike fighter with capabilities that no current adversary can fully match. The MQ-25 Stingray will extend the reach of the carrier air wing in ways that matter operationally. These are real advantages, and they are not trivial. But the carrier was optimized for a world where expensive manned aircraft were the primary delivery vehicle for air power at range. That world is changing. Cheap unmanned systems are proliferating faster than any major acquisition program can track. The ability to mass launch, accept attrition losses, and regenerate capability through numbers rather than individual platform quality is becoming a legitimate alternative to the expensive platform model. Not just for non-state actors or regional powers, but increasingly for major competitors. The Catapult paradox is a window into that larger tension. The machine that can throw a 50,000-pound jet cannot reliably throw a 500-pound drone. Not because the physics is impossible, but because the engineering was never fully completed for that weight range. Completing it requires time, money, and the kind of iterative operational learning that comes from actually deploying the capability at sea. The Navy is doing that work. It is not doing it as fast as the threat environment is evolving. Will the light drone catapult capability arrive in time to be relevant to the force structure of the 2030s? Or will alternative launch concepts, rail launchers, pneumatic systems, vertical launch adaptations, end up carrying the load while EMALS remains primarily a heavy aircraft system? The next few years of testing and procurement decisions will start to answer that. One thing is clear already. The carriers of the 2030s and 2040s will not look like the carrier air wings of today. The mix of manned and unmanned, expensive and expendable, heavy and light will shift. The catapult that launched a generation of Super Hornets will either expand to cover that future or become one system among several. The engineering path is open, the budget path is contested, and the timeline is tighter than any acquisition schedule was designed to accommodate. Here is the question that sits at the end of this analysis, and it is worth thinking about before you scroll past. The US Navy is choosing, right now, how to balance investment in upgrading a catapult system on existing carriers against investing in entirely new launch concepts for the drone-centric air wing that seems to be coming. Those two investments are not mutually exclusive, but they compete for budget, for engineering attention, and for political will inside a defense acquisition system that does not move at the speed of the threat. If you were the CNO today, Chief of Naval Operations, making the call, would you spend the money to fully expand EMALS down to the light drone weight range on the Gerald R? Ford and the John F. Kennedy? Or would you put that money into alternative launch systems, accept that EMALS is a heavy aircraft catapult, and design the next carrier class from scratch around what the drone future actually requires? Drop your answer in the comments. There is no consensus inside the building, which means this is genuinely open. The carrier air wing is changing. The catapult that defines it is at the center of that change. How fast, and in which direction? That is the story of the next decade of naval power in the Pacific. If you want to follow where that goes, stay with us. The next piece in this series looks at a different kind of range problem, one that lives not in the catapult but in what happens after the aircraft leaves the deck, and how far it can actually reach before the math stops working.